One of the main motivations to develop calculus, for Newton at least, was physics. In fact, his theory of fluxions basically means derivative with respect to time. You might have also seen and used the fluxion notation in physics. On a circle, if we revolve along a circular path, then the distance traveled follows this formula. This is because of the radian measure definition. In this formula, r is a constant, so the rate of change of s is proportional to the rate of change of theta. Here, we have the rate of change of distance traveled to be the instantaneous velocity, which can be represented by a vector tangent to the circle, specifically the magnitude of it. We can plot this magnitude of velocity against time on the graph. Then now we consider the area under the graph from t1 to t2, which is by definition this definite integral. Recall the Riemann sum we derived in the first episode in this series. We are approximating the area under the graph using numerous rectangular strips. In this case, the length of the rectangular strip represents the instantaneous velocity, and the width is the small time interval. Then the area of one rectangular strip physically represents the distance traveled during this small time interval if the object travels uniformly at that speed. But it will approximately be the real distance traveled. That means the sum of the areas of the rectangular strips is approximately the distance traveled between time t1 and t2. When the number of strips tends to infinity, this area under the curve would be exactly the distance traveled between the two timestamps. To save space, we denote S1 as the length of S as seen from the diagram at time t1, and similarly for S2, so the difference is distance traveled. And now by applying this formula as well as this on the right, we get this. Here, θ1 is the angular displacement at time t1 and so on, which is a rather uninteresting result because it is basically restating the fundamental theorem of calculus. However, we can make it much more interesting by considering the horizontal projection of s and v. By considering the integral of the horizontal component of velocity instead, it should give the horizontal displacement. Consider this diagram. Since the tangent and the radius are perpendicular, the sum of red and yellow angles in the white circle is a right angle. At the same time, the yellow angle is theta. If we now zoom in on this area, then we can find that the red and green angles add up to a right angle, and by combining all these, we have green angle to be theta. So Vx is V times sine theta. Because of this formula, we can substitute v to be r times the rate of change of theta, and the integrand is this expression. Let's say a particle is at an angular displacement of θ1 at time t1. Then after some traveling on the circular track, it is at an angular displacement of θ2 at time t2. Then the horizontal displacement is the length of this orange segment. This can be calculated by considering these two horizontal segments, which are of lengths r cosine θ1 and r cosine θ2 respectively. So the horizontal displacement is r cosine θ1 minus r cosine θ2. Notice that we haven't done any integration, since we have not considered any antiderivatives, but we derived the formula that is typically solved using integration by substitution, the integral equivalent of chain rule. If we consider the vertical displacement instead, we would have this similar integral. As an example, let's say the angular displacement changes quadratically with time, which implies that the rate of change of theta is 2 times t. So if we want to calculate this integral, simply consider this formula, and we would have the answer. Here, since θ1 represents theta at time t1, so θ1 is t1 squared, and the same applies to θ2. Even in this example, we have only used derivatives and not integration. This is not my original idea, but modified based on Kabir's answer on Quora, linked in the description. In fact, at the time of writing his answer, he did not even know any integration techniques like substitution, so problem-solving skills play a bigger role here than knowledge. There are something that falls into the scope of the series but not big enough to have their own videos, so this video on the end screen talks about those concepts as well as a summary of the entire series. If you enjoyed this video, give it a thumbs up and don't forget to subscribe to the channel. See you on the next video. Bye!